algebra students, Mr. Lawrence here, and we're going to continue our exploration of graphing square root functions. Yesterday, we learned how to graph a basic y equals the square root of x, or rad x if you like, and then we also talked about vertical translations, where if there's something added or subtracted outside, it shifts the curves vertically, either up or down. Well, what's going to happen if we add it on the inside? Okay, so here I have y equals the rad of x plus 3. Well, again, we're going to go ahead and make an input-output table. But the smallest value of my input-output table this time is not going to be 0. I might include 0 in my input-output table, but it's not going to be my smallest value. Can anybody tell me what my smallest value is going to be? Yeah, my smallest input is going to be -3. Why? Because -3 will cause the x plus 3 to turn to 0. If I go -4, I'll be outside of my domain because I'll be trying to take the square root of a negative in the real number system. Not possible. Now, I'm not just going to plug in 0, 1, 4, 9 because there's a plus 3 in here. So -3 I'm going to plug in. Then my next input, I think, is going to be -2. -2, because -2 plus 3. Hey, get out of there! Sorry, I'm just yelling at my son. No, check with mommy before you have a snack. My son is grabbing a snack, trying to sneak it and be quiet, but I caught him. All right, so -2 plus 3 gets me 1. I'll be taking the square root of 1. Okay, if I want the square root of 2, it looks like I'm going to want x to be 1. Excuse me, the square root of 4, because 4 is a perfect square. If I put 1 in here, 1 plus 3 is 4, right? I'm just using a little mental math here to help me pick my input and my output choices. Okay, and then let's see here. I want to take the square root of 9, so I think I'm going to put 6 in, because 6 plus 3 is 9, and my pen is developing a mind of its own. Look at it, just carry all over the place. Okay, and then if I want the square root of 16, I would have to put in 13, which isn't going to fit on my graph, so I'm not going to worry about it. So if I put -3 in, I get 0. Square root of 0 is 0, and this is really starting to get annoying. Okay, if I put -2 in, I get 1. Square root of that is 1. All right, if I put, oh, this is driving me nuts. Okay, if I put 1 in, I get 4. Square root of 4 is 2. And if I put 6 in, I get 9, so I get 3. So -3 is going to be at 0. -2 is going to be at 1. 1 is going to be at 2. And then 6 is going to be at 3, which, no, right about there. Okay, so I don't know if you remember way back to the absolute value graphs, that the number outside the absolute value caused a change vertically. If it was +5, we went up 5. If it was -2, we went down 2 with the v. Well, the same thing, yesterday we learned the same thing happens with these radical graphs, radical functions, right? But with those absolute value functions, the v's, the number inside the absolute value had the opposite effect. So when it said +4, we went 4 in the negative direction. If it said -2, we went 2 in the positive direction. And if you look, that's exactly what happened with this curve. Instead of being centered or starting here at the origin, there was a +3 in there, and it went 3 in the negative direction. Yeah. If it had a -3, then it would have moved to the right. So it moves the opposite of what you think, because it's where we want to get 0. Okay, well, what's going to happen with this one? Well, I think it's going to move 1 to the left and 5 down. So you know what I'm going to do is I'm not going to make an input-output table for this one. I'm going to make an input-output table for y equals the square root of x. And then I can put 0 and 1, 4, and 9 in. And of course, I will get 0, 1, 2, and 3. But each one of those points is going to move 1 left and 5 down. Where am I getting the 1 left? From the plus 1 underneath the radical. And where am I getting the 5 down? From the minus 5 outside the radical. So if I'm at 0, 0, I'm going to move 1 left and 5 down, which, oh no! Stop, you're killing me, Smalls. This is driving me nuts. I don't know why it's acting so goofy. All right, so it's going to be right about there. Okay, now maybe I'll just make it easier on myself here. And I'll clone that a few times. Okay, now 1, 1 would be there, except it needs to move 1 left, and oh no, 1, 1 would be there, excuse me. And then 1 left and 5 down would take me here. Okay, 4, 2 is here, and it will go 1 left, and then 1, 2, 3, 4, 5 down. 9, 3 is going to go 1 left, and 1, 2, 3, 4, 5 down. And so my curve will look like this. So I'm basing everything off the idea of y equals the absolute value of x, knowing that a number added or subtracted outside the radical causes a vertical translation, either up or down. Okay, a plus 7 moves it up, a minus 7 moves it down. But when there's a number added or subtracted inside the rad, that causes a horizontal translation in the opposite direction. So if I have y equals, say, x minus 4 minus 3, okay? So we're going to start with y equals the square root of x, know what that graph looks like. This causes a vertical translation of the entire graph down 3. This part here, if my pen would work right, this part here causes a horizontal translation for right, because it was minus 4, 4 in the positive direction. And so therefore I can graph it very, very easily. Okay, there's one more problem I want to go over, and that's actually in digits. So hold on, let me pause the video. Okay, so we're asked to graph the function I equals 1/2 rad p, which gives the current I in amperes. What's an ampere? It's the way they measure current, amperes. Okay, for a certain circuit with p watts of power. Okay, so these are the new labels we have to learn when we're talking about an application problem. Okay, we don't have to sweat it. Just look at the formula. I is in amperes. Okay, and the circuit has p watts of power. When will the current exceed 2 amperes? Well, the first thing they're going to do is they're going to make an input-output table. Okay, and so they're going to put in values for the power of watts. Okay, they're going to use their formula, and then they will have the current in amperes, which is what I is. Okay, and they make a note, since the radicand must not be negative, that's the number underneath the square root, the radicand, the domain of the function is p is greater than or equal to 0. So they're going to use non-negative values. So the first thing they do is they put in 0. Okay, and of course they get 0 out. Then they choose to put 10 in, and they get the decimal approximation. It doesn't equal 6/10 exactly. That's a rounded number because the square root of 10 is an irrational number. If I divide it by 5, I don't get 6/10. I get something very close to 6/10. And so they just rounded it. Okay, then they use 50. Similarly, they get 1 4/10, but that's a rounded answer. Then they use 100, which makes a lot of sense because 100 is a perfect square. You know, square root of 100 is 10. 1/5 of 10 is going to be 2 exactly. Okay, so it says, when will the current exceed 2 amperes? Well, when the power is over 100. Yeah, because now as soon as I go to 101, or any amount over 100, could be smaller than 101, I will end up in my calculations at greater than 2 amperes. Okay? Now when they make their graph, let me see, here we go. All right, so the independent variable is always along the x-axis, and that's your power. And then your dependent variable is your current, I. All right, and I think, did they put the labels on? Yeah, there they go. Okay, and since they're only asking for over 2, they just chose to go to 3. Now, they had to go all the way up to 100 to get 2, so they're counting by tens, if you notice. They're not counting by 20s, they're counting by tens, right? Because here's a space here. Okay, so let's see here. So they plot their points, and the graph looks like that. And there you go. All right, that's all I wanted to show you. That's it for the video. You should be able to finish the rest of the homework. School year's winding down quick, guys. Yeah, there's not much time left. All right, have a good day, everybody.